Alright, in this lecture video, we're going to talk about section 8.2, which talks about the law of sines. And as it says, all of the triangles that we have worked with so far have been right triangles. When we solved them, we were able to use our trigonometric ratios, the sine, cosine, and tangent. We were able to do that because each triangle had a right triangle. But what happens when we do not have a right angle within the triangle? And that is, what is an oblique triangle? So, a triangle which does not include a right angle or a 90-degree angle is what we're going to refer to as an oblique triangle. To solve an oblique triangle means we are to determine all angles and all sides of the triangle. To do this, we must use either the law of sines or the law of cosines. And in this section, we will be using the law of sines to solve oblique triangles. So let's take a look at the law of sines. So first off here, we can use the law of sines to solve some of these oblique triangles. But let's take a look at what the law of sines is first. The law of sines. If A, B, and C are the measures of the angles in any triangle, and if a, little b, and little c are the lengths of the sides opposite the corresponding angles, then here we have A divided by the sine of angle A is equal to B divided by the sine of angle B, which is equal to C divided by the sine of angle C. An alternative version of the formula can also be used, so simply just their reciprocals is also something that we can take a look at. So here, in the printout that I have of these notes, you can't really see this triangle here very well, so let me just try to color it in. So here we have this triangle. First off, this C right here corresponds to this angle C, A corresponds to this angle A, and capital B corresponds to this angle B. Therefore, little b is going to be the side opposite the angle, just like little a is going to be side opposite angle A, and side C is going to be the side that's opposite the angle C. So, if we go on to the next page of notes, we can use these concepts to take a look at some triangles that we might be dealing with, some oblique triangles. But before we can use these, it is necessary to consider when we can use them. To solve any oblique triangle, at least 3 pieces of information must be known. If S represents a known side of a triangle, and if A represents a known angle, so any side that we know is going to be S, and any angle that we know is going to be represented by A, then there are 6 possible situations where only 3 pieces of information can be known. The 6 possible cases are this. Here, again, we have a triangle. We can know a side and then an angle and an angle, known as side, angle, angle, where 2 angles and the side opposite one of the known angles are known. So here we know this side, the length of this side, and it's opposite one of the angles that's known. The abbreviation that we're going to use is side, angle, angle. We can know angle, a side, and an angle. So angle, side, angle, where 2 angles and the side between that angle, those angles are known. We're going to use the abbreviation for that as angle, side, angle. Then we can have side, side, angle, where 2 sides and an angle opposite one of those sides are known. So we have 2 sides and an angle opposite one of those sides is known. the abbreviation that we're going to use is side angle. Or we can have side, where we have two sides and an angle between those two sides is known. So side as the abbreviation, or SAS. We can know three sides, so side, so all three sides are known, so SSS. Or we can also know angle, or all three angles are known, and the abbreviation is going to be AAA. Now what's really important here is this. Because the law of sines uses proportions that involve both angles and sides, the following pieces of information are needed to solve an oblique triangle using the law of sines. 1. The measure of one angle must be known. 2. The length of the side opposite the known angle must be known. We have to have the second point as well. And we also have to have the third point. At least one more side or one more angle must be known. We have to have these three things in place in order to be able to use the law of sines. Therefore, the first three cases listed in the table above involve situations where this information is known. Therefore, the law of sines can be used to solve these three up here. Side angle, side angle, and side angle. Now, let's briefly take a look at the length of the side opposite the known angle must be known. And here we have for side angle, we don't know the length of the side opposite the known angle, right? Here, this side is in between these two angles. But we want to have a side opposite the two angles known. Well, we don't know the length of this side, and we also don't know the length of this side. So therefore, it might first appear that we do not know the length of a side opposite one of our known angles. But here's the important thing to remember, and that is that the angles in a triangle must add to 180 degrees. So in any triangle, if you add the angles together, the angles must equal 180 degrees. So therefore, if we know this angle right here, and we also know this angle right here from side angle, we know these two angles, we can use that then to figure out what this third angle is right here that I'm shading in dark. And if we can use these two angles, add them together, subtract from 180 in order to determine this angle up here, now we'll know an angle opposite the side of which we know the length. So therefore, number 2 is still fulfilled in side angle. Alright, so what we're going to do now is we're going to go over lots of examples where we're going to use the law of sines to figure out all of the angles and all of the sides of these first 3 cases right here. Side angle, side angle, and side angle. Let's go on to the next page of notes. Decide whether or not the law of sines can be used to solve each triangle. Do not attempt to solve the triangle. So we're just trying to figure out if we can use the law of sines to do this. So let's take a look at A. Seems like here we know the length of side C. Here we know the length of side B. And here we know the length of side A. So here it seems like we have side. If we have side, can we use the law of sines to solve that? And the answer to that is no. If we have side, 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 we're down here in this case. The law of sines we can only use in these three cases above. Another way of saying that is, one thing that must be fulfilled in order to be able to use the law of sines is that, number one, the measure of one angle must be known. We do not know the measure of an angle here, so we're going to say no. Number one is not met. We do not know the measure of an angle. All right, what about here? What do we have? Here it seems like we know the measure of this angle. We know the measure of this angle. And we also know the length of this side. So what we have then is side, angle, angle. And that is our first case, side, angle, angle. Now, some places you might see this written as angle, angle, side, right? As long as we're going in the same direction, we should be good to go if we're calling this angle, angle, side, or if we're calling this side, angle, angle. Either way, we can use the law of sines to do this. Typically speaking, what we do whenever we're trying to figure out if it's angle, angle, side, or side, angle, angle, it's usually we go counterclockwise. But either way, here we meet all of the requirements for these three things. In C, we have an angle here, we have a side here, and we have an angle here. So again, yes, we can use this, because here we're going to be dealing with the case of angle, side, angle. Or another way of saying this is we have all of these three things that are met. These three requirements down here are being met. Again, like we said before, we can use the fact that 180 degrees minus these two angles right here is going to give us angle B. So we can figure out that angle, which is opposite one of the sides for which we know the length. Alright, we will now solve a few triangles for each of the three cases where the law of sines can be used. First, we're going to look at side, angle, angle. So we have this case right here. Solve the triangle below, round your answer to 1 decimal place. So, first off, one of the things that we should do here is this. Since we know these two angles, we can very, very easily figure out angle B. And like I've said now a couple of times, the way that we can figure out angle B, since the angles inside a triangle must always add up to 180 degrees, we can take 180 degrees and subtract 76 degrees plus 44 degrees. Right? Another way of saying that is just to make sure that we're all on the same page here. I'm simply just subtracting the size of the other two angles, and therefore angle B is going to be equal to 60 degrees. Now one of the things that we can do is figure out side C, and side C divided by the sine of the angle opposite side C, so a sine of 76 degrees, is going to be equals to 9 feet over the sine of 44 degrees. So here we have 9 feet, here we have 44 degrees. This ratio right here is going to be the same as this ratio that we get from this angle on this side. Right? Again, from the law of sines, we know that C divided by the sine of capital C is equal to A divided by the sine of capital A. And that's simply just what I'm filling into this side right here. We can now solve for C. If we solve for C, we're going to get that C is equals to 9 feet times the sine of 76 degrees divided by the sine of 44 degrees. Oops, let me scroll up a little bit here. I'm just multiplying both sides by the sine of 76 degrees. And using your calculator, if you punch this into your calculator, you'll see that C is equal to 12.6 feet. Now, similar to what we had before, we can see that B over the sine of angle B is equal to A over the sine of angle A. So now we're going to try to solve for little b over here, which angle B is equal to 60 degrees, and A is equal to 9 feet. Angle A is again equal to 44 degrees. So now what we can do is we can solve for B by multiplying both sides by the sine of 60 degrees. And now again, using your calculator, we can get that B is equal to 11.2 feet. So both here and here, we utilized the law of sines, plugging in the values that we know, and then solving for the variable that we're trying to figure out. Here, it was first the side C, and here it was side B. All right, let's move on to the next page in the notes. As usual, I'm going to encourage you to pause the video, give this one a shot by yourself, and see then if you're getting the correct answer by restarting the video. Alright, next we will look at angle side angle. It says solve triangle ABC, where B is equal to 38 degrees, C is equal to 72 degrees, and side A is equal to 7.5 centimeters. Round all your answers to one decimal place. So let's first draw ourselves a picture to see exactly what we're working with here. Here I'm going to call this one A, this one B, and this one C. We're saying that angle B is 38 degrees. Angle C is 72 degrees. And side A, so the one opposite angle A, is 7.5 centimeters. So this is what we're dealing with. Just like we did before, we'll solve the easiest piece of information first, and that is what is angle A. We can take 180 degrees, subtract B and C from it. So we'll have 180 degrees minus 38 degrees minus 72 degrees. So angle A is going to be equal to 70 degrees. Now what we can do is we can take the law of sines. This right here is going to be side B, and this is going to be side C. And we can say that A over the sine of A is equals to, let's try to solve for side B first, B over the sine of B. This is our law of sines. And now we can plug in numbers that we know. We know that side A is 7.5 centimeters. Sine of A is now the sine of 70 degrees, which is going to be equals to B times the sine of angle B, which is 38 degrees. Therefore, if we solve for B, B is going to be 7.5 centimeters times the sine of 38 degrees divided by the sine of 70 degrees. So therefore, B is going to be approximately 4.9 centimeters. Now we can also solve for side C. And again, if we have A over the sine of angle A is equals to C over the sine of angle C. Again, we're going to have 7.5 centimeters divided by the sine of 70 degrees is equal to C divided by the sine of angle C, which is 72 degrees. Solving for little c, we're going to get that 7.5 centimeters times the sine of 72 degrees divided by the sine of 70 degrees, or that side C is going to be approximately 7.6 centimeters. So here then we have both the side B and C along with side A, gives us the three sides, and we know also the three angles, angle A, angle B, and angle C. So therefore now we have solved this triangle. Those are two of the three cases that we can use the law of sines for. Lastly, now we're going to take a look at side-side angle. And the last case, side-side angle, takes a little bit more work. Before we can solve a triangle given side-side angle, we first must make sure that we even have a triangle. Sometimes the lengths given in side-side angle, in a side-side angle triangle, may result in one triangle, two triangles, or no triangle at all. So we need to investigate the information given before we solve, and because we need to do that, it says, therefore, this is known as the ambiguous case. Side-side angle is known as the ambiguous case. So, let's take a look at this here. It says, let's start off with the proportion sine of angle B divided by the side of B is equal to the sine of angle A divided by the side A. And let's solve for the sine of angle B. So again, this right here is the law of sines. Now we simply just have the sines of those angles in the numerator as opposed to the denominator. Nevertheless, this is still the law of sines. And now it's asking us to solve for the sine of angle B. So here, if we do that, we're going to multiply both sides by the side B. And therefore, we're going to have sine of angle B is equal to little b times the sine of angle A divided by little a. Now let's take a look at this here for a second. This right here, we might have values that are going to give us these three cases. It says, because values of B, A, and sine of A are always positive. Now, why are they positive? This is the side of a triangle. The side of a triangle, we can't have a negative length. A is again a side of a triangle, so therefore we want to have that as being a positive length. And sine of A is going to be an angle, so again we want to consider this to be a positive angle. So therefore these three things are going to be positive. It follows that the value of sine of B is also positive. If all of these things are positive, then we must also have that the left-hand side of the equation is positive. Therefore, there are three possibilities for the value of the sine of angle B. And that's either that it's greater than 1, that it's equals to 1, or that it's somewhere between 0 and 1. But let's take a look at these three cases. Let's first take a look at when the sine of B is greater than 1. Recall for what that must mean if the sine is greater than 1. If the sine is greater than 1, we have no triangle. Remember back from our unit circle that we're saying that sine is going to go between -1 and 1. So therefore here, if we have a sine greater than 1, we can't form such a triangle, so no triangle exists. However, if the sine is exactly equals to 1, as we have in the second case, well, now the only time that that's going to happen is if our angle is 90 degrees, therefore we can only have one such triangle. Now, if we're in the third case, so the sine of B is between 0 and 1, here we can have one or two triangles. There are one or two possible solutions for B. Then here we can have, if there is one solution for B, then the triangle is oblique with 3 acute angles. What does it mean to have acute angles? Simply just means that the angles are less than 90 degrees. So all angles are less than 90 degrees with 3 acute angles. Or the triangle is oblique with 1 obtuse angle. And what does it mean for an angle to be obtuse? It simply just means that the angle is greater than 90 degrees. So we either have 3 oblique angles where each angle is less than 90 degrees, or we have 1 obtuse angle where that angle is greater than 90 degrees. However, if there are 2 solutions for B, which we're going to call B1 and B2, then the result is going to be 2 possible triangles that we can have. Alright, if that was so far clear as mud, don't worry about it. We're going to go through some examples, and we're going to show when we have each one of these cases. So let's go on to the first example. So here in the first example now, we have for each of the following, first decide if 0, 1, or 2 triangles exist, then solve the triangles. We have that A is equal to 10 feet, B is equal to 28 feet, and A is equal to 29 degrees. So again, if we have the sine of B over B is equal to sine of A over A, we can have that sine of B is equals to, sine of B over 28 feet is equals to the sine of 29 degrees over 10 feet. Solving then for the sine of B, we have that this is going to be 28 feet times the sine of 29 degrees divided by 10 feet. And if we do this on the calculator, we'll see that the sine of B is approximately equals to 1.4. So what we're saying here is that this right-hand side right here is about equals to 1.4. Which means that since 1.4 is greater than 1, where in this case right here, sine of B is greater than 1, or in this case above, the sine of B is greater than 1, we have no triangle. So here, I'm going to say, therefore, no triangle exists with these characteristics above, so we cannot solve this. So those two sides that we were given and the angle that we have simply just cannot create a triangle. Alright, let's go on to number 5. We have that A is equal to 13 centimeters, B is equal to 7.8 centimeters, and angle A is equal to 67 degrees. So let's first take a look at this here. We have the sine of B over B is equal to the sine of A over A. So therefore here we're going to have that the sine of B over 7.8 centimeters is equal to the sine of 67 degrees over 13 centimeters. Sine of B therefore is going to be 7.8 centimeters times the sine of 67 degrees over 13 centimeters. Therefore the sine of B is approximately equal to 0.6. So therefore here we're now in the third case. The sine of B is between 0 and 1. So therefore we can have, down here in this case, we can have one or two triangles. Right? One or two oblique triangles. So let's take a look at it to see what we have. I'm going to call this right here case number 1. And what we can do now is we can solve for B. And if we solve for B, right? So what are we going to do here? We're going to take the sine inverse of both sides. Therefore, what we're going to say then is B is equals to, right? So imagine that we're right here. If I take the sine inverse of this, we're only left with B. So therefore, I also need to take the sine inverse of the right-hand side. And we have this right here. So if you take the sine inverse of the left-hand side, you get just B. If you take the sine inverse of the right-hand side, you get the sine inverse of everything on the right-hand side. If you do this now, you'll see that B comes out to approximately 33.5 degrees. And I highly recommend that you pause the video and you give this a chance by yourself to make sure that you can actually get that this comes out to about 33.5 degrees. But now the important thing here is this. If we take angle A and we add that to angle B, which we just figured out, and we add that to some angle C, which we haven't determined yet, then this should come out to 180 degrees. So another way of saying that is this. We have 67 degrees, plus we just found out that we have 33.5 degrees, plus an angle C. Can we come up with that to be equal to 180 degrees? If we solve for C, it's going to be 180 degrees minus 67 degrees minus 33.5 degrees. So C will come out to 79.5 degrees. And that is completely an okay angle for an angle in a triangle. Now, if we're dealing with case 2, then we can say that B is again equals to the inverse sine of 7.8 centimeters times the sine of 67 degrees divided by 13 centimeters. And another angle that will solve for B is 146.5 degrees. Now, the important thing to realize here is that this right here is in quadrant 1, and this right here is in quadrant 2. So, if we take now, I'm going to call this B1, and I'm going to call this B2. So therefore, here we added B1 in here. I'm going to do the exact same thing now with B2. If we add the angles of the triangle together, it still should just be 180 degrees. Angle A is still equal to 67 degrees. Now we just found out that we have another possible solution being 146.5 degrees. If we add that to C, then we should get that the three angles of a triangle add up to 180 degrees. But if we now solve for C by taking 180 degrees, subtracting 67 degrees, and 146.5 degrees, we'll now get that angle C must be a negative 33.5 degrees. And this is not okay. We cannot have an angle for a triangle that's negative. So therefore, the first one that we found out is okay. The second one that we found out is not okay. So therefore, that means that there is only one triangle that we can form. So therefore, we only have one triangle that can be formed, and that is the triangle that for angle B is 33.5 degrees, and for angle C is 79.5 degrees. So therefore, we know the three angles, we know two sides. All that we still need to do is figure out side C. And using the law of sines again, we can see that C divided by the sine of angle C is equal to A divided by the sine of angle A. If we do this here, if you plug those things in, this is going to be the sine of 79.5 degrees is equals to 13 centimeters divided by the sine of 67 degrees. If you do the arithmetic, and I'm going to skip that here since we've already done that several times in this video, we're going to find out that C comes out to approximately 13.9 centimeters. So therefore, now we have all three angles and all three sides of this triangle. So therefore, we have solved this triangle. Alright. In question number 6, we're going to practice the exact same thing that we've practiced in question number 5. So what I would highly recommend is that you pause the video here and try number 6 by yourself. If you need to, rewind the video, watch number 5 again first, and then attempt number 6 by yourself. But first, here we have side B and side C and angle B. So therefore, what we can do is we can say that sine of C divided by C is equal to sine of B divided by B. We can have sine of C is equal to C times the sine of B over B. and plugging in values here, we're going to have 15.5 times the sine of 34.7 degrees divided by 11.3. These are inches. So therefore, we're going to say that the sine of C is approximately equals to 0.8. So again, there may be one or two triangles, since we are, again, in this case right here. We have one or two oblique triangles. So let's figure it out. How many do we have? We're going to call this case number 1 again. If we're trying to solve for C, right, here I'll write it down again. We have sine of C is equals to 15.5 times the sine of 34.7 degrees divided by 11.3. If we take the inverse sine of both sides, we'll get this. So therefore, here C, and we'll call this C1, is going to be approximately 51.3 degrees. If we take A plus B plus C1, sorry, you couldn't see that, so let me backtrack here. Took the inverse sine of both sides, which here on the left-hand side is just going to leave me with C1. On the right-hand side now I have the inverse sine of all this. If you plug this in using your calculator, you'll get that the inverse sine of all this comes out to approximately 51.3 degrees. So that's what we're going to call C1. If we add up the three sides of a triangle, those three sides should be equal to 180 degrees. We have that A, we know that from the problem B is equal to 34.7 degrees, and now we just found out that C is equal to 51.3 degrees. So therefore, if we solve for A is going to have an angle of 94 degrees. And that is an okay angle for a triangle, an okay angle for any triangle to have, right? Because we have these three angles now add up to 180 degrees, so that's fine. Now, we can also have case 2, and that is that I'm going to call this sine of C2 is equal to 15.5 times the sine of 34.7 degrees divided by 11.3. Now, if we take the inverse sine of both sides, we'll get, again, this, just like we had before. Now we can get that another solution to this is that C2 is approximately 128.7 degrees. Again, I highly encourage that you do this in your calculator. And we know that we can have two possible solutions to this given the characteristics that we have of the inverse sine. But again, the characteristics of the inverse sine, that was a previous section. So make sure that you're comfortable with the fact that we could have two possible solutions to the inverse sine here. Again, let's verify that this is a possible angle that we can have for a triangle. So if we take A plus B plus C2, we want to have that it's possible that adding those three angles we can get 180 degrees. We now have that A plus 34.7 degrees plus 128.7 degrees. We want to have this add up to 180 degrees. If we solve for A A is now going to be equals to 16.6 degrees. And again, 16.6 degrees is an okay angle to have in a triangle. So therefore, here we have two possible triangles that we can have. So, again, we're in this scenario right here, where the sine of B was between 0 and 1. In question number 5 above, we had that case, but we found that we can only have one triangle. Here we had a case that was not okay for an angle. Here we had a case that, here we had a case that was okay for an angle. Here we had a case that was not okay for an angle. So therefore, we only ended up with one triangle. However, down here, we again ended up with that sine of C was between 0 and 1. So again, we're right here. But here we have the case that we could have two possible triangles. So here now we have two solutions and we have two possible triangles. Alright, so now that we have two possible triangles, we need to solve both of these possible triangles. Let me get another piece of paper over here to make sure that I have enough room. So let's work with case number 1. So what we'll do here is I'll extend this down, and we'll first work with case number 1. In case number 1, what we can have now is we already know the sides of B, and we already know side C and angle B. So what we still need to do now is we can say, okay, if we have the sine of B over B, this now needs to be equal to the sine of A over A. We do not know side A, but we do know angle A, angle B, and side B. So therefore we have that the sine of 34.7 degrees divided by 11.3 inches is equal to the sine of 94 degrees over A. If we solve for A, then this can be equals to, or is equals to 19.8 inches. If we continue with case B, then we'll have sine of B over B is equal to the sine of A over A. Again, we'll have sine of 34.7 degrees divided by 11.3 inches is equals to now the sine of 16.6 degrees over A. And if here we solve for A, this will be 5.7 inches. So therefore, in these two cases, since we can have two triangles, here we can have our solutions be that A is 94 degrees and side A is 19.8 inches. B is going to be equal to 34.7 degrees and B is equal to 11.3 inches. And C is equal to 51.3 degrees and C is equal to 15.5 inches. Or in case number 2, we can have that A is equals to 16.6 degrees and side A is equal to 5.7 inches. B is equal to 34.7 degrees and B is equal to 11.3 inches. And C is equal to 128.7 degrees and side C is equal to 15.5 inches. So therefore, we have two possible sets of solutions that we could find if we start off the problem with side-side angle. Or angle, side-side, however you want to call it. But that's why this case is called the ambiguous case. Alright, let's move on to the next page in our notes. And it's asking us to now solve these word problems using the law of signs. So let's do it. It says, to determine the width of a river, forestry workers place markers on opposite sides of the river at points A and B. A third marker is placed at point C, 200 feet away from point A, forming triangle ABC. If the angle in triangle ABC at point C is 51 degrees, and if angle in triangle ABC at point A is 110 degrees, then determine the width of the river rounded to the nearest tenth of a foot. So let's draw ourselves a picture so we can wrap our heads around this. We have this river. This is a great looking river. Wow. Awesome. We have point A and we have point B on the opposite side of the river. And point C is 200 feet away on the same side of the river. So here, this distance is 200 feet. It's telling us that this angle right here at point A, this one right here is 110 degrees. So maybe this isn't the greatest picture. Maybe we can have it like, over here or something. But, well, why don't I just go ahead and change this here. Since I've already started off with such an amazing picture, no need to sell this thing short. Here now. Bam. Wow, great. Angle A in this awesome river that is just teeming with fish and people who want to get these amazing fish with their fishing poles. Alright, anyways, we have this triangle right here, and we know that the angle at side C, this angle right here, is 51 degrees. We're trying to figure out how the width of the river, how wide is the river. So we're trying to figure out over here side C. And it's side C because it's opposite angle A. So first off this, we can figure out this angle over here, angle B, because we know that A plus B plus C is equal to 180 degrees. A is equal to 110 degrees. Trying to figure out angle B, and angle C is 51 degrees. So therefore, B is going to be equal to 19 degrees. Using the law of sines, then we can say that C divided by sine of C is going to be equal to B divided by the sine of angle B. Then we can solve for C, and plugging in values that we know, this is then going to be side B, right? Again, this over here is side B since it's opposite angle B. This is going to be 200 times the sine of angle C, which is 51 degrees, divided by the sine of angle B, which we just found out to be 19 degrees. If we plug these values into our calculator, we'll get that this comes out to 477.4, since we're just asked to get it down to the nearest tenth of a foot. Alright, let's go on to the next problem. Again, I would recommend that you pause the video and give this one a chance by yourself. It says, Jack is on one side of a 200-foot wide canyon and Jill is on the other side. Jack and Jill can both see the trail guide at the bottom of the canyon. Jack sees the trail guide at an angle of depression of 60 degrees. Jill can see the trail guide at an angle of depression of 51 degrees. How far is Jack from the trail guide? How far is Jill from the trail guide? Alright, so let's again draw ourselves a picture. We have Jack and Jill at a 200-foot wide canyon. So we'll say that here, this is 200 feet. We have Jack and Jill. Alright. In this picture, I'm going to have that Jack has long hair, because there's nothing wrong with that. And Jill's going to have short hair. And maybe a hat. Short hair covered up by a hat. Perfect. Alright, so here we have Jack, and here we have Jill. And they see this tour guide. I'm not quite sure what this tour guide is. Or trail guide. Oh, it's a trail guide. Alright, so it's a trail guide. So here we have this trail guide. It says what kind of trails that there are and stuff like that. Alright, so here we know that from Jack, the angle of depression is 60 degrees. And from Jill, the angle of depression is 51 degrees. And we're trying to figure out how far away is Jack from the trail guide and how far away is Jill from the trail guide. So A and B. So we're trying to figure out. Alright, so let's do it. First off, we can figure out this angle right here, which is what we'll call angle C. And as we've seen before, we can calculate angle C by taking 180 degrees and subtracting angle A, which is 60 degrees, and angle B, which is 51 degrees. I'm hoping that all of you feel very, very comfortable with this right now. So therefore, we have that angle C is equal to 69 degrees. For Jack now, we can have that, excuse me, we'll have that 200 over sine of 69 degrees, right? Since this right here is 200 feet, we know that this over here is 200 feet as well. And here this is 69 degrees. So therefore 69, the sine of 69, or 200 feet divided by sine of 69, should then be the same thing as the side of B over the sine of 60 degrees. Right? Here is 60 degrees, sine of that, that's going to be this over here. I'm sorry, then we're not calculating out Jack. This right here should be for Jill. So let me articulate exactly what I'm doing right here. If I try to figure out this side B, that's how far Jill is away from the trail guide. To figure out side B, it's going to be B over the sine of 60 degrees. And our law of sines is going to tell us that this whole equation right here should be true. So if we solve for B, then B is going to be 200 times the sine of 60 degrees divided by the sine of 69 degrees. So B is going to be approximately 185.5 feet. Now, for Jack, we're going to figure out how far Jack is away from the trail guide. So we're going to try to figure out side A. And to figure out side A, we can have that A divided by the sine of 51 degrees is equals to, again, 200 divided by the sine of 69 degrees. 69 degrees and 200 feet. If we solve for A, we're going to have 200 times the sine of 51 degrees divided by the sine of 69 degrees. So therefore, A comes out to be 166.5 feet. So now we figure out that Jack, which is side A, is 166.5 feet away, and Joe, which is side B, is 185.5 feet away. Alright, and now the next page of your notes are our practice problems, but as usual, that is left for you. So therefore, this concludes the lecture video for section 8.2.